Thank you so much for the invitation. I'm really honored to be here, very happy. Throughout the years, I have met so many wonderful people that studied here, and I'm really happy to get to know the place and to meet some of the people that I know so well from years here in their own environment. So today what I'm going to talk about is I'll try to give an introduction about the area of printed electronics and try to show that printed electronics is not only about solution processing, but solution processing is a big part of it. And solution processing has very specific challenges. I'll try to point out some of the challenges and some of the directions that people took and some of the directions that I think people should start paying more attention to. Just as an introduction, I think Nir gave a good introduction, but when we think about printing, it's really, you are going to work with a new kind of materials. It's not the same type of materials that we have in microfabrication. It's a completely new technology. There are many exciting advantages of this new technology, and there are many things that can make breakthroughs. There are a few things that are extremely important and we are all excited about. So the first thing is that these materials are processed at a very low temperature. Because we don't have vacuum systems, we don't have high temperature depositions, we are printing things. Because they are processed at low temperature, that means that they can be processed in unusual substrates, which means that there is no silicon wafer. So there shouldn't, sometimes we do things on glass, but because of the low temperatures, we can also do things on plastics or paper. I believe what Nir was saying, that we have to merge the technologies, because of course if you want something that's flexible, you can sputter things at very low temperature, and that's compatible with printing, that's compatible with solution processing. So I think hybrid combinations are also making this area of flexible printed electronics important. There's a lot of work that is done in printing that is related to organic materials. And I think the fact that we have organic semiconductors really pushed the printed electronics area forward. Because these materials are flexible, they are polymers, they are flexible, and they can be processed at low temperature and from solution. So the main issue here, or the main big point here is that this technology really opens up new manufacturing opportunities. There are several areas that I think are already getting impacted by this technology, and I think many more are going to come in the future. So I have to talk about materials because I think this area is really an area that is highly influenced by the materials. And if we have been in this area for as long as Nir and I have been, we know that there were many materials that were developed in terms of organic semiconductors. But there are very few applications that people looked at. And it was almost like in a fashion wave, where first everybody worked on OLEDs. So all the materials that people were studying, the physics and the chemists were synthesizing huge amount of materials that were emissive materials for the OLED application, so emissive displays. Then there was the wave of TFTs, and everybody was studying TFTs, and materials were developed to optimize the transport in a TFT structure, and printing really took off because of TFTs. That's when people started seeing more and more publications about printing. It was the TFTs. And of course, 5 years ago or so, we had the wave of solar cells, where people start paying attention to solar cells, more materials came for solar cells. And we see the progress. It's amazing what happens because of these applications. What I want to show today is that I believe that this area is at a point where we can expand and we can look at other applications. And I hope that by the end I'll convince you that this is becoming a technology, a viable technology. But first, where are we? So if we look at the LEDs, the very first LED was not very efficient. It was just a crossbar type of contact and on glass. This technology today at the host center in the Netherlands is really disruptive, where we have LEDs of any color in a pretty simple structure using flexible substrates. The structure is still similar to the original LED, but people understand a lot more what's needed there. But what you can see is that it's really flexible and very bright LEDs. On the other side here, I have an even more simplified process that people developed for LEDs. And there's this company in the Bay Area called AddVision that now belongs to Sumitomo Chemicals, where what they did, what they developed was more of LEC, where they doped the light-emitting polymer layer, and they were able to produce these emissive materials also on flexible substrate. This was fully printed, only using screen printing. And a very simple structure that gave high brightness devices. And for a different type of application here, Philips and the host are more interested in lighting, so they go for large area, while here they were interested in signage. So you see that they go for color and not necessarily high resolution. So LEDs really gave a huge step forward, and it's a technology that we are going to start seeing, I believe, in the future. In terms of displays, as I said, there was a wave of the TFT, and everybody was working on these devices for flexible backplane. So the media was flexible, and it's mostly e-ink. And e-ink it was perfect for organic-based or printed TFTs, because it just needs voltage in order to switch. It doesn't need high current. So even though we had low mobility in these materials, we could provide the voltage that e-ink needs to turn. So you see, there were many demonstrations, including myself. I was working here. I also worked at Plastic Logic, so I influenced two of these demonstrators. But we never saw a flexible product that came out of this technology. And here, people were using different things. This was PVI was using a transfer technology, where they process everything on a rigid substrate and then transfer to the flexible substrate. This was developed by Philips, and then PVI bought it. And actually, this is the technology that's used today in our ebook readers. So if you destroy your ebook reader after you're done with it, and you have one of the new ones that are very lightweight, you will find that the backplane and the display media are flexible, but everything else is rigid. And that's why we don't have flexible products today. So that already gives us hints of where we should start working if we are students, and we should take those challenges, and otherwise we're not going to see flexible products. In terms of solar cells, this is the not complicated, it's just the map of very good research results for solar cells that NREL publishes every 2 years or so. I think this is the most updated one. And what's nice for this printed area or organic electronics is that if we zoom in here, only in the year of 2000 we started seeing this technology in this map. Which is very important, but that tells us how young this technology is. And we see how the advantages, the advances that are happening here, and this really comes from the materials. People understood the physics, and the chemists made much more efficient materials. And here we are approaching film technology, efficiencies. Very exciting for this area. But there are challenges, right? As I said, these three technologies were the main driven forces for printing and for organics. But if you think about it, they all require long-term material stability, long shelf life stability, process reliability, and because we are making things that needs to last for years. I don't want to change the solar cells every year, certainly not every week. I don't want to buy a new display every year or a TV. So we really, these applications are very hard applications to work on. And if we think about technology as we know today, there's always a workhorse semiconductor. What do I mean by that? We know what CMOS is made of. It's a one type of semiconductor. It's one process. We know what a green inorganic LED is made of. We know what a blue LED is made of. In organic electronics and in printed electronics, that doesn't exist. Everybody works with whatever semiconductor their chemist who is a friend will give to them to work with. That makes it really hard for the technology to advance. And then there is the process that by many people, by many of us, or many of you, I don't do that, who are refereeing papers and are editors, view processing as not scientific. So if I work in printing and I am trying to make a semiconductor behave well so that I can say exactly how the transport works and how you can make something useful with that material, it will be seen by many editors as not scientific. Oh, this is just, oh, you're just trying things. And that's a problem in this area that I'm not happy with. And I think if you think about it, it's really important problem to work on. Because how can you predict and control properties of materials if you're not working on processing? So I really think that this area needs to start learning from inorganic electronics, which is why people were capable of taking that building size of computer and putting inside a laptop, actually putting inside a phone. Our phones are very good computers because they worked on processing. Because there is a recipe for, and there is a model for film deposition, for shrinking resolution, and really push the technology forward was by making the processing reliable, and then you can design products. So I think that's an opportunity for this area, for solution-based electronics and for printing. And I truly believe that it's helpful to focus a little bit on applications that are going to take advantage of what we always write in the first paragraph of our papers or our proposals, that this technology is important because it will enable flexible, printable, low cost. So let's work on that. We have light emission in every wavelength of the spectrum right now because of the LED development. We have very high light absorption with just a nanometer film. We can absorb an immense amount of light with organic materials. In every wavelength too, and but we have low mobility, so that's just admit we have low mobility and be creative of what we can do with these three things which have been pushing other applications right now. So I believe we should work on the non-problems. We should really be honest about the problems, and short-term material stability is a problem in this area. So it's great that there are so many chemists that work in this area because I believe they can solve that problem together with engineers and physicists that give feedback on the device. Same goes for the short life, shelf life stability. But as I mentioned before, I really think that process reliability is a must. You see, I already broke something. It's a must, and the lack of work-hard semiconductor is a problem. So sometimes we need just to pick a material that will give us reliable process, and then try to push the boundaries with that material, as opposed to be always chasing the highest efficiency solar cells or the highest mobility TFT. These are all my personal beliefs in this area. So, so the way I've been looking at printing technologies is really as a tool for the Internet of Things, which is something that is coming. It's very clear that we are going to have wireless sensors everywhere. We are much more dependable on our mobile devices, and our mobile devices depend on more infrastructure that will give us always connectivity, always the updated information that we want. And printing could be a tool to build this hardware that's needed for the Internet of Things. In order to do that, it's good to demonstrate devices that are ready for the technology, and maybe picking things that are slightly easier than a display might help to bring the technology faster. So, what are the questions that we have been asking ourselves? That's a difficult question. Okay, why do I do printing? I love to work on printing technologies. That's not good enough. So you have to say, where do you really need to print something? Because of course, microfabrication is here and it's not going to go away because it works so well. So we shouldn't try to take microfabrication away. But printing is very good for large area systems. So photovoltaics, for example, displays, imagers. If I really want to have a display that is as big as this screen, that is actually part of this building, that is part of the wall, I think printing could contribute to that. I think printing is very good for distributed electronics. Places like these wireless sensors that I mentioned, if I want to put electronics in very low density over large areas, printing could be a good way, where you can have sensors, maybe a simple amplifier, not really very high computational right there in that location, and just distribute over areas, or over large areas. For security, there are many people that want distributed electronics over large areas. So the holy grail, and what we all talk about, is about row-to-row fabrication, really monolithic integration, where you are continuous depositing the material by printing and forming these different devices. But I think that there is a lot of space for heterogeneous integration, where you can really merge printing with the technologies that we know today, such as microfabrication. So I'm going to give you an example of one project that we are doing this. We are integrating, we have heterogeneous integration, where we use silicon chips where they are very good at, and we use printing for what printing is very good for. And then I'll give you examples throughout the talk. So this is a vision that came out of the Berkeley Wireless Research Center, which is the era of the unpad. So right now we all carry computers and phones. Some people carry 2 phones, one for work, one for home, and we have lots of devices that we carry. So this group at BWRC has the vision that in the future, these computers and mobiles, these physical devices, are going to disappear. And everything that we need in order to interact with our data, what's our data, our email, our music, our videos, phones, phone calls, and so on, will be done, will be part of the infrastructure of the buildings that we have today. What we are doing there, we are thinking about, these guys are really experts on the wireless technology, and we are thinking about what is the physical platform that can support this. on top of the software platform. So if electronics are really going to disappear, and disappear in the sense where we are going to be wearing things, hopefully not so many wires hanging from us, we saw in Las Vegas 2 weeks ago on the Consumer Electronics Show, where people were really talking about wearable devices. That was the hype of the meeting. And so if electronics are going to be integrated with our bodies, and with the buildings, what is it that you need? Of course, it needs to be extremely low power. We need always to power this electronics. And you always have to have a constant wireless link. For the new generation, there's nothing more annoying than going somewhere where they don't have a wireless or they don't have Wi-Fi. And this comes from my son, who is only 7 years old. He's like, no, let's not go to that restaurant. They don't have Wi-Fi. So I think this is something that's important, this has to be part of the vision. So what are the solutions that we have for this particular subject? We are looking at places or applications and designs where we keep the link to wireless very short, we are leveraging the space. So always have, instead of having transmission over long ranges, we're just putting antennas in closed space so that we have a very short link to the connection. How are we doing this? As I said, we are leveraging the space, and we call this electronic wallpaper project. Or the idea is that we are designing these antennas, as I said, so that we have shorter links, and the antennas are printed, some of the connectors that need to carry more or be faster and carry more current, we do with etched copper, because that's what's the best for now. We print the antennas, and then we integrate silicon chips here with the functionality that we want in corners. And with that, we are merging these two technologies to give us a new application. The idea being is that if we put wallpaper in the walls, you could put the different designs. So here we could put antenna arrays, you could put displays, you could put imagers, you could make electronics part of the wall. But first you need to know how you are going to connect and what's their constraints. So this is one of the first applications that we have. So we have done quite a lot of work on the design of the ICs, and this I do in collaboration with BWRC. So Elad Alon and Jan Rabai and John Warsnick, who are the designers of the IC and the system. What we are doing in our group is really looking at how can I put that silicon chip that's rigid in a flexible substrate that has printed electrodes and printed antennas on it in a way that I can truly flex and carry it around and transport without the silicon chip popping out, which, believe me, it happened many times. So today, oh, this didn't come out very well here. Today we are at a stage where we have the connectors. We got the process for the printing down so that it doesn't get damaged when we are integrating with the silicon chip. You can see here the silicon chip and our connectors, and these connectors go to big antennas, and this is an array of antennas and silicon ICs. And here you can see how much you can flex that substrate, and the silicon chip stays put. You get an idea of the scale here by the fingers that are holding that. So that's just one example of heterogeneous integration. Okay, and large area. So now, when does it really need to be flexible? That's the other question for printed electronics, because printed and flexible always go together. They're confused with each other sometimes. I truly believe that when you have human body contact, flexibility is important. We are flexible. We don't like to wear bulky things. And if we are going to be wearing the electronics, of course, flexibility is important. And again, for large area electronics, flexibility is also important because it's more robust. It doesn't break. There's no glass. And it's easy to transport, it's easy to install. And of course, this has been the reason for so many people work on flexible solar cells, not only in organics, but in all technologies, people try to get flexible solar cells just because it was easy to transport and easy to install. And of course, medical devices, I'm going to talk a little bit more about that project. So I have two examples of human body contact and what we are doing here, where we are printing and where we are not. So for wearable devices, the first thing people want in wearable devices is to measure vital signs. So vital signs, you want to measure temperature, blood pressure, pulse rate, respiration rate, and blood oxygenation. When you go to the hospital, first thing they do, measure your blood pressure, your temperature, and stick this device in your finger that is measuring your pulse rate and your the blood oxygenation. Turns out that the way this measurement is done, you have two LEDs and one photodiode. It's a very noisy measurement because you only have a point source, this photodiode, measuring the light that is transmitted through your finger. Or through your earlobe. So you need quite powerful electronics because the signal to noise ratio is not really good. So you have to amplify the signal, you have to filter things, and you have to average the measurement and so on. Now, printing is very good for putting devices over large area. Printing, you can print the same thing over and over again. So what we are doing here is that, as I said at the beginning, you have LEDs that emit light in every wavelength of the spectrum, and we do have materials that absorb light. So why can't we just improve the way that this measurement is done by making the data more available by making arrays? So now you have redundancy in your data if you have lots of photodiodes and lots of LEDs that are printed. And then it doesn't need to be in your finger. It doesn't need to be only through transmission. It can be through reflection. And I could be wearing this even under my sleeves, and nobody would need to know that I am monitoring my health signs, that I am worried about my health to the point that I need to monitor it. So this is what we have been developing. So what are the challenges here? Now the lifetime is not as bad as a display. But what's important is that I need enough brightness so that I will get the information, so either goes through the body or it reflects enough that I can measure. But I need a specific wavelength. I really need to have a material that is tuned to give a very sharp emission at the wavelengths where I need to do the measurement. Same goes to the photodiode. It needs to be a very good photodiode for 2 wavelengths. And here's how this measurement can be done. So if you look at the molar excitation coefficient of the blood, there are distinct differences between the oxygenated blood and the venous blood in a certain wavelengths. For example, here around the red and here around the infrared. Also around the blue and the green, there are big differences. So that's why you need 2 LEDs. You illuminate your finger with 2 different wavelengths, and then you measure with the photodiode, and you calculate the ratio. It's not as simple as this, but you have to subtract some of the background information, but that's how the measurement is done. When you look at the whole system, the system level design, and I really think that it's important to look at the application that you were working on just to decide what can you do and what you cannot do with printing. So there are devices which are the front end here, is there are devices. You need light emitting diodes and photo detectors. And I truly believe that we can do that with printing technologies. Then you have some analog devices where you are converting the system before you do the processing of the data. Those, I think we could have by printing. Today, this has not been demonstrated because the amplifiers are not so good when you print. But maybe merging photolithography with printing could get us closer to this. This part here, which is the computing or the digital part of the system, I really think you just do with a silicon chip because that's nicely done there. And then again, where you need to see the data, especially us humans, we want to see what's going on. If we are monitoring, if I'm wearing this, I want to know. That data could be sent to my phone if I'm carrying my phone, and many people do that, so you can download in your phone. Many of the exercise type of devices do that. But it could also have a display there. That could be done by printing, and people have shown that that's possible. All right, so if I'm going to work on the devices, that means now I need flexible devices, which means that our good old structure for LEDs and for solar cells is no longer what I have to work on because it has glass and it has this transparent film, which is ITO. And those things are not flexible. So if you truly want to have flexible electronics, you cannot have ITO anymore, you cannot have glass. So the first thing that we did was, okay, we start with this, which is where people have published tons of paper in the literature, so we can always compare to. And we worked on changing the substrate and changing the ITO contact. So we have been working with this company, Linde Nanomaterials. They are mostly selling gas. They're from Germany, but they are also looking at other materials. And they developed carbon nanotube solutions that can be deposited through different solvents, organic and aqueous dispersion. And for the longest time, we were trying to match the characteristics of ITO. ITO is a great transparent material. It has very low sheet resistance, and that was our target. If you take ITO and the best ITO on PET that we found is this point right here. You see it's not as transparent anymore and the sheet resistance is higher now. The catch is you touch this ITO, it breaks, and then it's not even in this plot anymore. So we looked at these carbon nanotubes and we say, okay, it's very hard to match ITO. We could never match that figure of merit. But we went ahead and studied the devices. And when you look at the characteristics of the devices, so this, again, the active layer here, we made solar cells. The active layer was P3HT PCBN. So if you look at the characteristic of devices, here is the ITO compared to the carbon nanotubes. They are very flexible. You can bend them as much as you want. This is not going to change. The transmittance, a lot, well, not as good as ITO. But the device efficiency and everything else in the device was exactly the same. So you cannot look at a material in isolation. Okay, exactly the same. I'm counting like the variation device to device. You can't see a big difference. So you can't look at a material in isolation. You have to look for the application, and the application we wanted was LEDs and photodetectors, and here's the photodetector. So any losses and what was not good in the device was coming from other layers, not necessarily the carbon nanotubes that was being here substituted by substituting the ITO. Okay, so that's one layer of the device. The photodiode, the specifications for the photodiode, now we don't want solar cell, we want a photodiode. We have a specific wavelengths where we want this photodiode to work. Of course, you need very low noise because the signal that I'm taking for this measurement is a very tiny AC signal that is in the big background of the blood signal that you get, which is DC. The AC is because it's pulsating, right? Our blood is pulsating. And then you also need a good response in the red and the infrared frequencies. So I already told about the benefits. So I work with Antonio Facchetti from Northwestern University in Poliera. And he said, well, I have this material. It's not the most efficient solar cell, but are you sure you want it? I said, yeah, because it has good absorption in the infrared. And that's what we were looking for. And we also worked with this material in PCBM too, or PC70BM, because of the band gap here and how the energy levels aligned, it had better absorption towards the infrared. I'll show you the performance soon. So the first thing we did was to take the first material and really optimize the process. Because we all know that the process makes a big difference here. And here what I'm showing is that we changed the solvent ratio, we changed the donor to acceptor ratio to really make the best diodes that we could. We tested them as solar cells because that's what people are used to read in the literature. And we chose the best processing conditions here and the best donor to acceptor ratio in order to process these devices. In terms of the spectral response, which is what we were looking for, the first material that I showed you, it was more efficient overall. And they're even more efficient now when we understand the device a little bit more. But the second material actually showed a flat absorption here going from the red to the infrared. And in the end, we chose to use that material, even though the other one was more efficient, because this one was better for that application. The LEDs, I'm going to tell you up front, they're not as good as the photodiode, so they have more challenges, and we have better materials now. But what we started working on was in this tri-blend system where you get the red emission from this material and you use the other materials for injection and energy transfer. So here you can see the properties of these materials. These materials are very well known. We have worked on them for years. And we never found a material that would work well on the infrared for LEDs. But when we look at the curve of how you do this measurement, there was a place around the green, and that also could work. So that's what actually we have been using. We have been using the green LEDs with the same materials. We just take the red emitter out of the blend, we adjust the ratio, and you get very good green LEDs this way. Also, nothing new here because these materials have been around for a long time. So we have green and red, and with green and red you can do the measurement with reflection instead of transmission, and I'll show you how it looks like. As I told you, the photodiodes are really good. So here what we did, first we learned to do the measurement by taking the conventional photodiode, the silicon photodiode out, and using only the printed, this was printed photodiode to do this measurement. And you can see here that you get very nice response here from your heart rate, and you can measure the oxygenation of the blood, heart rate, and here's the oxygenation. When we put the organic LEDs, this is with the red LED, doing the same type of measurement with the red LED, and here doing the same type of measurement with the green LED. There's improvement that's needed, and we are working on that now. And this is coming mostly because the emission of the green and the red is quite broad, and it's quite broad here, so they overlap. So if we had emission that was narrower, that measurement would be cleaner, basically. And that's what we are working on now. Okay, I think I'm doing okay in time, so I'll talk about another application. And this is a work that I have been doing with one of the Technion students, who is now a professor at UC Berkeley, and his name is Mickey Lustig, and he is a specialist on MRI. This project only happens because he has his office next door to me. He saw me talking at faculty lunch, and he said, you know, one of the biggest problems we have in MRI is because the hardware is not flexible. Do you think we could work together and solve that problem? And I'll show you how a very good example where you need something to be flexible and printing makes sense. So here's the typical MRI. Right? I always have to say this because whenever I say I'm working on flexible MRI, people say, oh, I don't need to go on the big tube anymore. No, the tube stays there. That's the magnet. And you lay down on this bed, and over here there are transmission coils, RF transmission coils. So you need magnetic field and you need RF field in order to do the measurement in MRI. Usually, the medical systems operate at 1.5 Tesla or 3 Tesla. There are other systems for research with very high fields, like up to 12. But the common in hospitals is 1.5 and 3. And that's what we are developing this hardware for, or this flexible ware for. So when you go and take an MRI, this is how you look like. Except that most people are not smiling. They are really freaking out because they are going to go into that machine. Kids have general anesthesia. Many people need general anesthesia because they just can't handle it. And you have this cage on top of you. And this cage is quite heavy. These are the receiver coils. So you have transmission coils underneath you, and then the receiver coils are on top, RF coils. It's very uncomfortable. I had this done for myself just to get the experience. So what's problematic here? So these coils are designed for a 6 feet tall guy. If you are not that person, if you're not 6 feet tall, you have problems. If you're taller or shorter, that's not going to fit you very well. The kids have a cage that it doesn't touch them because this is heavy, so they don't want to touch the kid. So the kids have a cage that is really far away from their body. So when you go into the machine, there's a lot of calibration that needs to happen because they need to calibrate for the signal, the MRI signal that everybody gives, and it's different. And because of that calibration, the coils have some play on them. Okay, because the kids are so far away, it just takes longer and longer for the scan. And the data is not as good, so you need to acquire more data, and it takes a long time to do that. So, and here's I will show you an example. So if you take a coil, and you place the coil in the neck, for example, which is a curved area, and you go and you do, there's no offset from your body, and you do a scan, you see how good the image is, which means that here you have very good SNR. So this scan can be faster because you have good match with the body. Now, if you offset by 3 centimeters the same coil and you do the same scan, you see here what happens to the image. Now, if that cage doesn't fit me very well, doesn't fit kids very well, doesn't fit many people very well, these are the type of things that you're going to see. Where what we want is to have the clearest possible image because we want to see what's wrong with us. So here's, I'm going too fast. Here's what we are doing in this. We are printing arrays of coils. You need arrays just to get better coverage. We are using screen printing. And the idea is to have T-shirts that have these coils, and you go to the hospital, you dress with your T-shirt. Everybody knows the size of T-shirts, and that will fit very well. And then all you need to go, when you go to the room, you connect to the machine, and it's a lot more comfortable, and you have better fitting to your body, so you get better imaging. What do you need in these coils? The coil is an antenna. It's an RF coil, so you have an antenna, you need conductors, and you need capacitors, two types of capacitors. One that you are going to use to set up the input impedance that needs to match the body, around 50 ohms. And the other one that you're going to use to tune to the resonance frequency, which is dictated by the machine that you have. If you have 1.5 Tesla, you're going to have 6.4 megahertz. For 3 Tesla, you have 128 approximately. So a lot of the work that we did here for printing was, of course, to learn how to print these coils on a flexible substrate, and also to tune the dielectric so that we would get the capacitance that we need and be able to match for the different frequencies here. We have 3 scanners available for us. One is a 3T and one is a 1.5T. Of course, you have to book, takes time, so we develop for both and we use whatever is available. So how do you know this is working? You have to tune, as I said. So of course here you have the tuning circuit, and this goes to the MRI machine. And here you see how you have the peak frequency here for the tuned coil, exactly for 1.5, which was what it was designed for. The ultimate testing in imaging is really to go and image. So here's my student and our collaborator at Stanford, and they have a phantom, which has basically salt water that mimics the chemistry of our body, and you put the flexible coil around it, and then you image. We always compare with what's traditional, and you can see here, GE provided the phantom, so here you can see the production coil, the type of image that you get, and here you can see from the printed coil, the type of image that you get. Not bad. So I'll stop here, just 2 more slides. The fun test for students, of course, there's a machine, there's a student, there are coils. We want to get images that are cool. So here is how we place the coil, and here's how it's interfacing to the MRI machine, which always amazes me. This is like 3-layer printing on a piece of plastic, and here's what you can get. It's a healthy 23-year-old knee. Which apparently looks very good. It looks much better here, but there's nothing I can do about that. But it really shows how you don't need to make a whole new technology in order to use printing and flexible. You just have to be watching what's needed here and work with what is available. So I'll skip this because I already talked about this, so I hope I convinced you about these points. And of course, I have to acknowledge the people that fund my group and believe in that I'll do something smart with it. We are funded by NIH and several other agencies and companies. I have to especially acknowledge Mickey Lustig, who's my collaborator in the MRI project, and the professors from BWRC, who are also my collaborators, and of course the people that give me the materials that I need to do this research. And thank you very much for listening.